Hello and welcome. In this example, we're going to look at the difference between voltage drop and voltage to ground and how we can use our voltage divider equation to get both of those for us. So first thing we need to look at is what they're asking us for, and they want us to know what VA, VB, VC, and VD are. And those values are marked here by our probe lines. This is VA, VB, VC, and VD. And if we look at our circuit, we can kind of guess on two of these. We can say that the 9 volts here is leading directly up and touches this probe line here. No resistance in between, which means we didn't lose any voltage yet. So VA should be 9 volts. And if we continue on down, we see that VD is at the very end. It's actually touching our ground location. So that should be 0 volts. It shouldn't have any voltage potential left at that point. So we can use those two immediately determine those. So we know that by the end, we get 0 volts, and at the beginning, we have full voltage. So now we just need to figure out what happened to VB and VC. And that has to do with our voltage drops. Right, so we know that this resistor is going to consume some of our voltage. We can call that VR1. And we know that the second resistor here is also going to consume some of the total voltage of 9 volts, so that's going to be VR2. This last one here is VR3, right? It's also going to consume the remainder of whatever voltage is left over. So we need to figure out those, because once we figure those out, we can use KVL, which states that if we know our voltage source, we can subtract the voltage that we know we lost, and we'll end up with the voltage remaining, and that'll be VB. Right? And once we get VB, we can say not voltage source anymore, but VB minus the voltage we know we lost, R2, and that will be VC. And that's going to give us all we need there. And then at that point, whatever VC has is what VR3 is going to be. So we kind of know that one at that point. Okay, so that is our goal. We're going to find 2 voltage drops here using our voltage divider equation, and then we will apply that to the KVL equation to solve for the voltages B and C. So want over have is our ratio equation for our voltage divider. And write want over have. That's how I remember it. And then that's multiplied by your voltage source, the thing that you want to divide. And so since we are looking for R1, the first resistive drop in the circuit, we can say that our want has to be R1, right? We want to know the voltage drop across R1. So we'll put R1 in terms of our want for our resistor. And then on bottom, we'll put what we have in the circuit. And what we have is actually RT. So we don't actually know that yet. We got to go solve for that. So let's do that first. We'll say RT equal to, and since this is a series circuit, we know that that's going to be the sum of all of our resistors. So it's R1 plus R2 plus R3. We'll plug that into our calculator and solve for RT, and that will allow us to solve for the voltage drops across each of these components here. So R1, watch out for this. R1 is 1,000 ohms. It's 1 kilo ohms. And we can't just put a 1 in there. We actually need to put 1,000, right? Because we have a 240 ohm resistor after that, and that's not in kilo ohms. We also have a 720 after that also. So if we put a 1 there, we would have gotten a much smaller number than if we put 1,000 in there. So watch out for your notation when you're solving for your total resistance. But now we know. Now we know RT is actually equal to 1,960 ohms. We could plug that in for what we know for RT up here. We can say that it's 1,960 ohms on bottom, and that's what we have in the circuit. And R1 we know, right? That's 1,000. Make sure you put all your zeros in here if you didn't put the bottom in notation. 1,000 on top for R1, that's what we want to know the voltage drop across. On bottom is what we have in the circuit, total resistance. Then we multiply by our voltage source. We have that still. That was given to us at 9 volts over here. So we'll plug 9 volts in for our voltage source. Then we'll solve for that. Out and we'll say that we have 1,000 divided by 1,960. That's a ratio equation. And if we stop here and we look at this ratio, this number output, this 0.5, that has to be less than 1. If it's greater than 1, you've probably done something weird with your equation. You might want to go back and look at your 2 resistances and make sure you didn't accidentally flip the equation upside down, or make sure you've gotten your total resistance on the bottom there. Okay, now that we double checked our ratio, we can multiply by our 9 volts times 9 here, and that gives us 4.59. We can say that VR1 is equal to 4.59 volts. 4.59. Okay, so now we can apply KVL, our first KVL thing. We now found out VR1, we know the voltage source. So we can say that we have 9 volts minus 4 0.59 volts, what we lost across that first resistor, and that's going to give us our VB location. So that we started with 9, we lost 4.59, and now we have 4.41 left. 4.1 volts. This is 4.41 volts, right? So out of our total voltage, 9 volts, our first resistor used up almost half of our voltage, just over half. That makes sense. That makes sense because that resistor is the biggest one, and so it should consume the most amount of voltage overall. But now we're moving on. Now we now have VB in this equation here. We can plug in 4.41 volts for VB. We can even write it up here. 4.41 volts is what VB equals. Right, moving forward, we can say that we just need to figure out VR2 to subtract from that, and that's going to give us VC. Let's do that. We can use the same voltage divider equation. We can say that we know that VR2 is equal to want over have. We'll put R2 as what we want to know. Have is going to be RT. We'll multiply that whole thing by our voltage source. We know all of these values. We know R2 is actually 240 ohms. So 240 on top. We know our RT did not change. Right? Still exact same circuit that we just were dealing with. So we can use the same RT. 1960 there. And then our voltage source also did not change. It's still 9 volts. So we can solve this out and determine the voltage drop across R2. We can even use the same setup that we did in this previous one because our resistance on the bottom did not change and our voltage did not change. So as long as we just swap out the value of our R1 resistor here, we'll be able to solve for that. So we'll put 240 here instead of 1000. Gives us 1.1 volts. That is the voltage drop across R2. VR2 equal to 1.1 volts. And so now we can plug that in down here. We can say that our VB was equal to 4.41 volts. That's what we had left at that B location moving forward. And after our R2, we end up at our C location. So we'll subtract what we know we lost across R2, which is 1.1 volts. And that's going to give us the remainder. That's going to give us VC. Right here, we'll say that we have 4.41 minus 1.1, 3.31. 0.31 volts, our point C location, 3.31 volts. So again, if you were to go in multisim, build this circuit, you would be able to measure from this location to ground and get 9 volts. You would be able to measure from the B location to ground and get 4.41 volts. And then you'd be able to measure from the C location to ground, get 3.31 volts. And then at D, you should see that ground is ground. It is 0 volts at D. That's all we needed to do. Let me know if you guys have any questions about that.